Welcome back to the Cave of Science, and I want to do a couple of the problems that are going to be on the assessment on next Wednesday for the Kepler's laws. And the first one I want to look at is the determining eccentricity. Remember, eccentricity is d over L, where d is the distance between the foci, or sometimes you'll hear the pronounced foci, where L is the length of the major axis. Length of major axis. This goes back to the worksheet we did where you did all the ellipses. And if you remember, you drew some ellipses. So this would be this distance from here to here. This would be D, and then the major axis is from the aphelion to the perihelion, and this distance would be L. So if you have those two distances, you can determine how oval or how circular the ellipse is. So let's just say, for instance, we have the distance between the foci are 5 AUs. So that's that distance. And let's just say our major axis is 10 AUs. And again, we're in the solar system, so we're using astronomical units. So E is D divided by L, or 5 AUs divided by 10 AUs. And those will cancel out. And 5 divided by 10, I get my calculator out, and I think that it's going to be 0.5. So 0.5. That's the eccentricity. As this number approaches 0, the ellipse becomes more and more circular. So make sure you recognize that fact. The other problem, and we did this one in class, flip this over. Did this one in class, was the problem number 8 on the back of that worksheet. This is where we had an ellipse, and I'll draw the ellipse here, and we have our foci here, and again we have our major axis running through here. So we want to determine either the distance from perihelion to the sun, and remember, in this the sun is always one of the foci here, foci, and we did this one, or you could determine from the sun to the aphelion, which is the farthest point away. So you can really do either of those. So for this particular problem, we're going to say the eccentricity equals 0.19. That is our eccentricity for this particular problem here. We're going to say the distance between the foci, this distance, so that would be D equals 0.4 AU. And let's just say for this one, we're going to find the distance between perihelion and the sun. We don't know this, so I'll just call this X. We do know the distance between the sun and the aphelion, and we're going to call that 1.5 AU. So really, we've got to find this distance, but we can't find, let me move this down a touch, we can't find this distance unless we know L. We don't know L, so we need to find that. So we know our formula is eccentricity is the distance between the foci and divided by the length. So we can go ahead and plug this in. So 0.19 equals, we know D is 0.4, and I'm not going to put the units in on this one, over L. And this is our typical cross multiply and divide, so I'm going to put this over 1. So 0.19, and I'm going to bring it up here. So 0.19 L equals 0.4 times 1, which is going to be 0.4. So L is going to equal 0.4 divided by 0.19. So 0.4 divided by 0.19 equals 2.10. 2.10. And again, the units is going to be an AU. So that's L. That's our whole distance here from perihelion to aphelion. I just want this distance. So I can take the length, 2.10, minus, I have this distance already from Sun to aphelion, 1.5, and if my math is correct, this comes out to be 0.6 AU. So this distance would be 0.6 AU. So once you got the length, if you wanted to find this distance, just like we did on problem number 8, you can go either way with this. But you've got to calculate the length, so you have to be given the distance between foci, and you have to have the eccentricity. The last problem that's going to be on the test is really dealing with Kepler's third law. And Kepler's third law stated the square of the period, let's move this down a little bit, equals the cube of the distance between the Sun and the orbiting object. So there's only two possible ways to do this. Let's say P, and again this is going to be in years, is 3 years. So very easily you can substitute that in. So 3 squared equals A cubed. 3 times 3 is 9 equals A cubed. At this point, you've got to make sure you know how to operate your calculator to find the cube root. Because to solve this, you got to take, well, the cube root of A cubed is going to be A, but then you got to find the cube root of 9. Now my calculator, and again, everybody's calculator is a little different, so you got to know how to operate yours. On mine, I've actually got a button for this. So I can go 9 second cube root equals, oh, there it is right there, which is about 2.1. So A would equal 2.1. Pretty easy to check that. Times 2.1 equals times 2.1 equals, I'm pretty close. And again, this would be in AUs. Or you could go the other way. So we still got the same formula. And let's say we were given a distance of, let's just say A equals 4. So we're going to say A equals 4 AU. So we know P squared equals 4 cubed. P squared. So we got a cube 4. So I'm just going to go 4 times 4 equals times 4 equals 64. Okay. And from there, we got to take the square root. So P equals the square root of 64. And that should be fairly easy to find on everybody's calculator. So I do have a square root key here somewhere on mine. I can quickly find it. There it is right there. So I've got 64 square root, and so P equals 8 years. Excuse me. So those are the three you're going to find on the assessment on Wednesday. All right. That's it, and we'll talk to you later.